Hello, calculus fans. This is a particular skill about trig functions that is of general interest, but in particular, it's very helpful when you're doing trig substitution and you're doing integration. And it's often something people forget. So I'm making a separate little video just about this. And often maybe you've just never had a reason to think about this. So reminder about trig, where it all started with right triangles. And the observation that if you have a right triangle that's big or small, but has the same angles, the ratios are the same. And we can use this to do all sorts of things. But anyways, somebody's like, well, there's 6 ratios. There's B over A, there's A over B, there's B over C. So there's all these. So we gave them a name. So some students know this as SOHCAHTOA, I think is how they tell me it. I didn't learn that when I was a student. But it's opposite over hypotenuse. And so opposite over hypotenuse would be B over C. So if you happen to have a triangle that's a right triangle, and you know the angle, then you also know this ratio. And this is adjacent over hypotenuse, so A over C. This is opposite over adjacent. And these are just the flipped version. This is 1 over cosine. This is 1 over sine. Sorry, this is 1 over sine. This is 1 over cosine. And this is 1 over tangent. There's a separate thing, which we should also know about triangles that ties in with this, which is that a squared plus b squared equals c squared. And occasionally in what we're going to be doing, we're going to want to be solving for c, which would be a squared plus b squared. Occasionally we're going to want to solve for a, which would be the square root of c squared minus b squared. Occasionally we want to solve for b, which is the square root of c squared minus, and I'm just rearranging this. So I've never actually done this before, but I think I'll just make a note. This is the square root of a squared plus b squared. This is the square root of c squared minus b squared. This is the square root of c squared minus a squared. Okay, that's it. That's our fundamental. Let's get rid of that. That's our fundamental pieces. So how is that useful? It's useful in the following way. So maybe I'll start with an example to sort of review a few things. This is what I always remember, this example, and you might appreciate this in more than one way. So if I draw this equilateral triangle, it's 2 by 2 by 2. I happen to know that the angle is going to be 60 degrees or pi over 3. If I chop it in half, I get a right triangle. So this is just a funny little review of something you already know. So this would be 2, this would be 1, because it's half of that. But I don't know what the other side is. This is pi over 3, 60 degrees. So you could say, well, I can figure it out. This side is the square root of 2 squared minus 1 squared. So this side is the square root of 3. So there, we just used that fact. In addition, what can I say about this? Well, I can say cosine of pi over 3, in no particular order, is 1/2. So there's yet another way to remember this. My students in my class know I've given many ways to remember this. I personally like the unit circle, but there you go. You could always just draw this equilateral triangle and figure this out. Similarly, tangent of pi over 3 is opposite, so it's square root of 3. And you could get all the other ones, right? So you have secant of pi over 3 is equal to 2. And you can keep going. But once you know one of these, you know all the rest. Okay, so here's how we use this in calculus, is we often encounter things where we know a certain substitution. And what we're going to do is we're going to rewrite it as a fraction. And we're going to label. So we're going to draw a little triangle. What happens in these problems is we often need to know one of the other trig functions. So we're going to label x and we're going to label 2. So if you know how I did that, opposite, adjacent. And we're going to solve for the other side, which we can now quickly see is 4 minus x squared. I just used this. And now we know all the other trig functions. What is cosine of theta? It's adjacent over hypotenuse. There's the adjacent, there's the hypotenuse. What is secant of theta? It's 1 over cosine, so that's this idea. It's a very valuable idea for going between your trig functions. Because of this, we never write cosine of sine inverse of x over 2, because that is the same as this. So in math in general, we never write an inverse for trig inside of a trig. There's some problems with that in some situations, but it also is just much uglier and harder to work with. Okay, and we are going to expect that in our calculus courses, that you can write this version. So don't write this. This is a no-no. Okay, let's try it again. These are super fast. You can try on your own. Here's a triangle. You would say tangent of theta is x over 3, so you would say opposite over adjacent. You would solve for the other side, 9 plus x squared. And then whatever trig function you need, let's pretend you needed cosine for some reason. You would say adjacent over hypotenuse. Done. Let's keep going. I have 3 more. These are super fast. So what if you had x over 4 is secant of theta? Then you would draw a triangle, label an angle. I always just remember that this is 1 over cosine, so it's hypotenuse over adjacent rather than adjacent over hypotenuse. So it's going to be x, this is going to be 4, and then I solve for the other side, which is the square root of hypotenuse minus 16. Notice if it's a secant, you're going to see this minus after the x squared. If it's a sine, there's going to be a minus before the x squared. So after you do a few of these, you start to see some patterns. So then if the question said, what is sine of theta? You would say x squared minus 16 over x, opposite over hypotenuse. Similarly, if it's a little more complicated, you're just going to write x over 3. X plus 3 over is this. You're going to draw a triangle. This is a really fast thing to do. It shouldn't be, we don't want it to be a confusing thing. Opposite over hypotenuse. This side's going to be the square root of 25 minus x plus 3 squared. And then you could say whatever you wanted. You could say tangent of theta is x plus 3, which is the opposite, over this terrible mess. 25 minus x plus 3 squared. And there's one other comment I wanted to make is sometimes if you just rewrite it like this, you have fractions. Since we're talking about ratios, you could also get rid of the fraction, meaning multiply top and bottom by 2, or you can multiply the original equation by 2. If you multiply top and bottom by 2, you're going to get 2x plus 1 over 6. That's perfectly fine to simplify first and then draw your triangle. It's the only other thing I could think. It is fine to also use the original one, but you would say this is 2x plus 1. You would say this is 6. That's opposite adjacent. You would solve for the other side, which is going to be the square root of 6 squared plus 2x plus 1 squared. And then you can get any of the other trig functions you want. For example, cosine of theta would be 6 over this mess, which I don't want to write. That's it. That's the triangle trick. It's nice to just separate that. So if hopefully that was helpful. Let me know if that is helpful to have this separate